Hello students, welcome back to JCE Connect series of lectures. In this particular lecture, I'll be taking a design of gusseted base. In previous lectures and all, we have solved a simple slab based plate design. In this particular lectures, I'll be taking the design of gusseted base. So what is the difference between the simple slab base and the gusseted slab base? As I explained earlier, in a simple slab base, a simple base plate will be provided underneath the column. So underneath the column like this, a simple base plate will be provided, and that base plate is welded with the machined edge column, and that plate is been using only to take the lighter uh, side load coming on the column. And in this particular uh, uh, plate, that is a gusseted base, when the load coming on the column is on heavier side, or the load is accompanied with any moments, in that case, to take care of that load uh, and distribute on a wider area of the concrete pedestal, a gusseted base will be using. Okay, that is the difference. So here given, when the load on the column section is too large, or when the axial load is accompanied by a bending moment, when it is accompanied by a bending moments, usually a gusset plate is provided. It consists of base plate, two gusset plates, and sometimes some additional plates will be using along with the gusset plates, and two gusset angles when bolted connections are made. Okay, see, I'll repeat. When the load on the column section is too large, this one, when the load on the column section is too large, or when the axial load is accompanied by a bending moment. If it is accompanied by a bending moment like this, if it is accompanied by bending moment also, by bending moments, as well a gusset base is provided. So when the bending moment will act here, when the load is deviating from the centroid of the column. If the load is not acting axially, if the load is acting away from the centroid by some eccentricity, in that particular case a moment will be acting along with the load. That is, direct load is a P and the moment is M, and because of the moment a bending stress will be producing in the column, and because of the direct load P, a direct stress will be producing underneath the column of base plate. So because of the heavier load coming on the column, as well as if the load is accompanied by a bending moment, then a maximum stress will be acting at this particular zone. So it may fail at this point at this particular junction. So to prevent that from failure, additional plates will be using on either side of the column like this. I'll show here like this. Okay. So in this particular, this is a concrete pedestal, and this is the column. This one is the column, and this column is provided with the gussets. These are the gussets. As just provided the plates on either side of the flange. This is a flange, and this is a flange. This is a web. And here gussets are provided, and gussets are connected with angles. This is called gusset angles. This one, gusset angle, both side gusset angle. Sometimes along with the gusset plates, uh, uh, one more additional plate will be provided, that is the flange plates will be provided if the load coming on the column is very very heavy, then additional plates will be provided, and that plate width will be equal to the flange width. Okay, then these angles are called as a cleat angles or the gusset angles. Since these angles are connected to the gusset, hence the name gusset angles. And if the angles are connected to the web of the column, these are called web angles or web cleats. And these are called holding down bolts. These holding down bolts are connected to the base plate and the concrete pedestal. Base plate and the concrete pedestal on all the corners. I hope you understood this one. This is the flange and this is the web of the column. And for the flange, the gusset plates are provided along with the angles. And gusset flange, gusset plate and the angles all together connected by bolts here. Okay, so we need to design such kind of column providing the gussets and gusset angles. Okay, this is a cement concrete base. I hope you understood this picture. Then, so here given it consists of a base plate, two gusset plates, this one and this one, two gusset plates and gusset angles. These are the gusset angles. Then anchor bolts. Okay, so this is a pictorial view of that is a front view of the gusseted base. This is the side view given here. Okay, so now we need to design this type of a column base, that is gusseted base. What is the design procedure here? The design procedure will be to calculate the bearing strength of the concrete. Again, the same design steps to be followed as we followed in case of a simple slab base. Again, we have to calculate here also the bearing strength of the concrete by using this formula. In some of the textbook, they have taken this as a 0.45 FCK also. That is also correct. And both are correct. Okay, but as per IS 800-2007, this formula has been given. In some textbook, they use the bearing strength of the concrete by taking 0.45 FCK. Okay, then calculate the area of base plate required. The area of base plate required once we know the bearing strength of the concrete. Then the factored load divided by bearing strength of concrete, because the plate is resting over the concrete pedestal. So we need to take the bearing strength of concrete, that is load by pressure. Load by pressure gives you the area required. Then once we get the area of the base plate, then we need to calculate what is the length and breadth of the base plate. Assume the size of the gusset material and it should not be less than 16 mm in thickness for the bolted base, gusset base. Then the gusset angle is chosen so as to accommodate two rows of bolts. So here, whatever the gusset angle is chosen, so when you connect this gusset angle to the gusset plate, then when you provide the number of bolts here, it should accommodate two rows. So this leg should be wider. This leg, vertical leg, should be wider. And hence you need to choose an angle in such a way that it should accommodate two rows of bolts. Hence you need to choose unequal angle size here. That's why that's been given here. Okay, the angle, gusset angle, is chosen so as to accommodate two rows of bolts in the vertical leg and one row of bolt in horizontal leg. Therefore, an unequal angle section is provided. The thickness of gusset angle should be almost the same as that of the gusset plate. So it means, see here, this is the gusset. Whatever thickness you choose for the gusset material, the same thickness to be chosen for the angle. And angle to be chosen in such a way that the vertical leg which is connecting to the gusset plate, it should accommodate two rows of bolts. So this leg should be wider and the horizontal leg should accommodate one rows of bolts, and horizontal leg is connected to the base plate. Okay, So in such a way you have to choose the angle. It should be unequal angle section. Okay. Gusset plate. Okay, I hope you understood this one. The gusset angle is chosen so as to accommodate two rows of bolts in the vertical leg and one row of bolts in a horizontal leg. Therefore, an unequal angle section is provided. The thickness of the gusset angle should almost same as that of the gusset plate. Then you have to calculate length of the gusset material that is required. That is, length of the gusset material is normally kept equal to the length of the base plate. So here this one, this gusset material length, if you take from here to here, so whatever the width of the plate is here, the same length to be provided for the gusset. This length is equal to the length of the gusset plate. Okay. The length of the gusset material is normally kept equal to the length of the base plate parallel to the flange of the column. See, this gusset parallel to the flange of the column. This is the flange. This is the flange parallel to the flange of the column. This width or the length of the gusset is equal to the length of the column base plate. Then for welded gusset plate, gusset angles will not be required. For welded gusset angles will not be required. Then the dimensions of base plate parallel to the web. Then the dimensions of the base parallel to the web. How you can calculate the parallel to the web? Depth of the section. Here. How you can calculate? This is the web. This one is the web of the column. How you can calculate? Depth of the section from here to here plus 2 into thickness of gusset material plus 2 into leg length, this one, plus overhang. Okay. So how you can get, so here given depth of the section plus 2 into thickness of the gusset plate. This is parallel to the web. Depth of the section plus 2 into thickness of the gusset plate plus leg length of one angle, then overhang. This is bolted connection. This is for bolted connections. Then the welded connections, depth of the section plus 2 into thickness of the gusset plate plus overhang, because here angle sections are not providing in welded connections. Angles are omitted here. So you have to take depth of the section plus 2 into thickness of the gusset plate plus overhang. That is for welded connections. How it will be? So I'll show you. If you take suppose this is the base plate. This is the base plate. This is the base plate. Then on this base plate, this is the column. This is the column. Then this will be thickness of the column flange. You can see the thickness of the column flange. Okay. Like this, thickness of the column flange. And the next you get additional plates to be providing if required. These are called as flange plates, two sides. After the flange plates, then gusset plate, like this. Both side gusset plate. Then after the gusset plate, gusset angles, like this. Gusset angles. I hope you understood this one. Gusset angle. So this is up to here depth of the column, that is D. Then you will get thickness of plate, two thicknesses. Then you get thickness of here. Here you get thickness, depth of the section, column section. It is parallel to the web. Then you get, this is depth, then this will be the thickness of the plate on either side. This is thickness, this is thickness. Then the thickness of gusset, then the length of the angle leg, then you will get overhang, like this. Okay, then it gives you the length of the base plate. Okay, after calculating depth of the section plus 2 times the thickness of the plate provided for the flange, then the 2 times the thickness of the gusset thickness of the gusset material, then 2 times the leg length, this is outstanding leg of the angle up to here, then the overhang, this will be overhang. Let us go take it as a this also A. Okay, I hope you understood this one. Parallel to the web, depth of the section up to here, then 2 times the thickness of the plate, flange plate provided, then the 2 times the thickness of the gusset material, then the 2 times the leg length plus overhang. Okay, that is same is given here. Here, depth of the section plus 2 into thickness of the gusset plate and plus 2 into thickness of plate, also additional plates will be providing sometimes, plus leg length of angle plus overhang, that is for welded connection. Then the depth of section 2 into thickness of gusset plate plus overhang, plus this is for welded connections. So once we get the length, then we know area equal to what? B into L. Then B can be easily calculated. It is B equal to A by L, because area already calculated, required how much area to be required. Then also we have calculated one side dimensions, one side dimension that is parallel to the web. That parallel to the web dimensions were calculated based on the sectional, that is section properties, that is depth of the section, 2 into thickness of the gusset plate, leg length, overhang. From this we have calculated one dimensions, and other dimensions can be easily calculated. Okay, I hope you are understanding this one. Then once we get the dimensions of the base plate, then as usual we have to calculate the actual bearing pressure acting on the concrete pedestal, that is factored load, whatever the load is given, divided by actual area of the base plate. Okay, then calculate the thickness of the base plate required, and here the thickness of the base plate is required we have to calculate based on the moment criteria. That is, the thickness of base plate required is computed by equating the moment at critical section to the moment of resistance of the gusset at that section. Thickness of base plate required is computed by equating the moment at critical section to the moment of resistance of the gusset at that sections. Means here what happens, uh, bearing pressure will be acting, so like this. This will be a bearing pressure. Let us this bearing pressure will be W dash. Actual bearing pressure will be acting. So what happens, the load is coming on the column. This is a heavier load coming on the column, so it will apply maximum pressure on the base plate. Then the base plate may bend like this. It may be like this. Base plate may get, if you draw base plate layer, so at the center the load is acting, the base plate may bend like this. Okay, this is the bending of a base plate. So at the center the load is acting heavier, so this side it hogs. Suppose if it is accompanied with a moment, then this side pressure will be acting more, then this plate get lifted up like this. This is the plate. Sometimes this plate may get lifted up and it will be the maximum load will be acting at this particular point because it is accompanied with a moment, so it may press this side of this side portion of the plate, so maximum stress will be acting at this particular point. So here the plate may fail. So considering this, that is the root of the angle section, the critical section is assumed to be lying at the root of the fillet of the angle section. This is the root of the fillet of the angle section. So this may, at this particular, this is the most critical section. Say XX is a critical section. This is XX because the plate may get lifted up like this because of the heavier pressure acting. The plate may get lifted up, or this side may get lifted up. When it may get lifted up, so this will be most critical. This root of the fillet of the angle, and this is the critical section. Now we have to calculate for a moment about the critical section. We have to calculate moment about the critical section. Then this moment we have to equate to the moment of resistance of the plate. I hope you're understanding. When we calculate the moment at XX, because the XX is the most critical section. If failure to be happen, it will fails here. So center portion will be pressed. Then this side may get lifted up. Also this side may get lifted up. Then the plate may fail here at the root of the fillet of the angle section. Okay, this is the most critical section. Then moment about this we have to calculate. Then that is to be equated to the moment of resistance by using the pure bending theory. That's why it's given. So the thickness of the base plate required is computed by equating the moment at critical section to the moment of resistance of the gusset at that section. So we have to calculate moment at XX, then the moment of resistance. This moment of resistance to be calculated by using pure bending theory. M by I equal to E by R F by Y. So by using this we have to calculate what is the moment of resistance. Okay, so once we equate moment of resistance of the gusset to the moment actually acting at a critical section, we will get the thickness of base plate required. Okay, so how to calculate the moment of resistance and moment at xx? So that I'll take next part of this lecture. So these are the steps we need to follow for the design of gusseted base. Okay, so try to understand this gusseted base here. So these many materials will be using column section, then the additional plates will be using, then the gussets, this is additional plates, these are called the gusset plates, then the angles which are being connecting to the gusset material, hence they are called as the gusset angles. Then this is the overhang. Okay, hope you understood this one. And remember, the critical section will be acting at the root of the fillet of the angle section, at the root of fillet of the angle section. That will be the most critical section for the gusseted base. Okay, and suppose if it is accompanied with a moment, then we have to take the uh, direct stress plus bending stress. We know this formula in RCC. I think you have been studied P by A plus or minus M by Z. So where P by A is a direct stress and this will be the bending stress. From this we get two types of stress, that is one we get a maximum stress, one we get a minimum stress. Okay, so for this condition, if you take for this uh, suppose this is the uh, base plate and this is the column. If only one load, that is P, is acting, if I take this end as a and B, and whatever the stress distribution you get underneath the column, that is uniform, like this you get, and whatever the stress we get here is from this end to this end, that is P by A. Okay, if suppose the base plate, on the base plate column is resting and the load is acting P and it is accompanied with a bending moment. The bending moment is, if suppose the load is acting eccentrically, we get a moment as P into E, that is nothing but moment only. So because of this, what happens, the stress distribution underneath the column you get like this. Sometimes you may get like this. When you get like this, because we have a formula that P by A plus or minus M by Z. So this you get when M by Z is 0. When this is not there, that time you get only P by A. That is, this is the uniform stress distribution. When you get this one, you get this type of when P by A is greater than M by Z. Okay, so one side you get a sigma minimum, another side you get a sigma maximum. Then another pattern you may get, suppose this is the base plate and this is the column, it is P and they're also acting a moment. One more pattern again the same. What you may get, you may get like this, that is sigma minimum and sigma maximum. When you get this pattern, when P by A is equal to M by Z, this you get. Okay, one more pattern you get like this. Then this becomes sigma minimum and sigma maximum. So that is plus minus. When you get when P by A is less than M by Z. See, these are the conditions of pressure diagram underneath the column. So this type you get only for the direct load, direct stress. The direct load is coming and it is passing through the center. So the stress distribution is uniformly underneath the column. If suppose it is accompanied with a moment, when the moment will come, when the load is acting eccentrically, that is away from the center, in that case, if P by A is greater than M by Z, we get this type of a stress distribution. And when P by A is equal to M by Z, and P by A is less than M by Z. So we never ever should have this type of a stress distribution underneath the column. So it should be between these three only. So in all the time you should have this step, at least this. Okay, so the we never ever have this type of a stress distribution. It will create the tension at the bottom and hence leads to the failure. So this is not preferable, this type of, at least we should get this one, or at last the stress should be zero at here. It should not go in a negative side. So always this should be preferable. Okay, I hope you understood this one. This is a stress diagram. If moment is involved, we have to take this formula and calculate the stresses underneath the column. If moment is not there, then this becomes a zero. We get this type of, so this type we have solved in previous lecture, that is simple slab base. In simple slab base, when the load is coming on the column is light and passing axially or through the center, that time we were having only uniform stress underneath the column. This type of problem is simple slab base. And